Good day, everyone. You are all welcome to Fluid Mechanics lecture. In our today's topic, we are going to be looking at flow through pipes. Now let's look at the definition of what a pipe is. Flow in pipes refers to the movement of a fluid through a closed conduit or circular passage due to a pressure difference or gravity. There are three types of flows. We have the laminar flow. Flows in pipe occurs in three different forms. We have a laminar flow, we have a turbulent flow, and the last one is a transitional flow. In a laminar flow, the movement of the fluid particle is very smooth. That is, a laminar flow is a type of flow in which the fluid particles move in a definite path. So in this case, the speed at which the flow of the movement of the liquid is moving, as well as its Reynolds number, is very low. The second one is a turbulent flow. From the word turbulent, turbulent simply means anything that involves or something that comes in form of chaos form. So in a turbulent flow, these are types of flow in which the fluid particles move in an indefinite form. That is, a fluid particles that move in a 3D form. Now in this case, what happens to the Reynolds number and the velocity? The velocity at this level is very high, and its Reynolds number it increases above 4,000 in values. And the last one is the transitional flow. In a transitional flow, these are types of flow that is about to transit from the laminar flow to the turbulent flow. If you are using a Reynolds number, for example, to determine or to define this type of flow that I have just mentioned, for the first one, a Reynolds number is a dimensionless property which is represented mathematically on the board as RE rho UD over mu, where RE is the dimensionless properties, which is also known as Reynolds number. Rho is the density of the fluid. U is the speed at which the fluid is moving in the conduit or the pipes. D is the diameter of the pipe, and mu depends on the types of fluid that you are trying to convey. Mu is referred to as the dynamic viscosity of the pipe. Now let's take a schematic, a simple schematic in illustrating this. We have two types of flow. When we are analyzing, we have a compressible and incompressible flow. For a compressible flow, this occurs when the density changes. A typical example is when you are trying to consider some manners of flows that occurs in gases or gas or air. For incompressible flow, these are types of flow in which the density changes. So a typical example is water. Water is an incompressible fluid. Now for this schematic we have on the board, this is a pipe. Definitely the pipe will have a length L. Then also it has a diameter, the diameter of the pipe. Then the speed at which the water is being conveyed from section 1 prime to section 2 prime. This is V. Now, I've said something earlier on that the dynamic viscosity depends on the nature of the fluid. When the fluid is moisty or thick in nature, the dynamic viscosity in such case follows the non-Newton's law of viscosity. Are we together? Newton's law of viscosity is expressed mathematically as shear stress equals to mu du dy. We are not going into this, but I was only trying to explain how we have this relationship on the board. So if you are using a Reynolds number to define the three types of fluid that I have mentioned above, in a situation whereby we have it lesser than 2000, when Re is less than 2000, when Re is less than 2000, we have a laminar flow. When it is more than 4000, we have a turbulent flow. And when it lies between the 2000 and the 4000, we have a turbulent flow. If it lies between the two, we have a transitional flow. Now, for you conveying water from state 1 to state 2, there could be a form of losses that occurs. This is now what we now take us to the various types of losses that occurs in pipes. Types of losses or energy in pipes. Energy losses in pipe. We have two forms of energy losses in pipe. The first one is due to major head loss, and the second one is minor head loss. For the major head loss, two great scholars, they were the ones that contributed to this. The first one is named Darcy Weisbach, and the second one is Darcy Weisbach equation. The second one is Chezy formula. So how is this two related? Before we go into that, let's quickly look at what happened in this case. Major head loss is as a result of frictions that occurs in the pipe. And these two key things is going to be what we are going to be using in determining the head loss. Now, for Darcy Weisbach, the mathematical expression is given as H subscript F will be representing the head loss in the pipe. HF equals to 4F LV square divided by D multiplied by 2G. How do we arrive into this formula? Each of these terms will be illustrated in this simple schematic. This is the length of the pipe, which is showing here. The speed at which the water is flowing, that is the velocity. Then we have D. D is the diameter of the pipe, which is as shown here. Then G is acceleration due to what? Gravity. Then also we have F. F in this case is called friction factor. F in this case is known as friction factor, and it is defined as F equals to 0.00791 divided by Reynolds number raised to the power of 0.25. Reynolds number raised to the power of 0.25. Then for the second one, which is Chezy formula, we are going to look at the mathematical derivation of the Chezy formula. But its formula is this. Let me just put down the formula on the board. V equals to C into brackets MI. V is known as the speed or the velocity at which the fluid is moving in the pipe. C is the Chezy Chezy constant. M is referred to as hydraulic mean radius, and this M can be determined depending on the shape of the pipe you are analyzing. If, for example, we are analyzing a circular pipe, the hydraulic mean radius is defined as the area is the ratio of the wetted area to the perimeter of the pipe, which is given as M equals to A over P. This is referred to as the wetted area, and P is the perimeter. Now, how do we determine this? For a schematic of this nature, we all know that the area of a cylinder is what? Pi what? R square, or pi D square over what? Over 4. What is the perimeter? Perimeter is what? 2 pi R. 2 pi R. So we can reduce this equation down to this. Pi cancel pi. So we have what? R over 2. If it is in terms of diameter, we know that diameter is how many of radius? 2 of radius. So this equation later becomes D over what? Over 4. So the hydraulic mean radius is given at the expression you have on the board. Derivation of Chezy formula. Now let's consider the schematic I'm about to put on the board. This is the pipe length, the pipe diameter, the pipe speed, the pressure, now we are going to apply the Bernoulli equation at state 1 and state 2. So the Bernoulli equation in the mathematical form is expressed as P1 over omega plus C1 squared V1 squared over 2G plus Z1 equals to P2 over omega plus V2 square over 2G plus Z2. We need to take some forms of basic assumptions while deriving the Chezy constant. Number 1, the flow is steady. The flow is steady and continuous. The second one is the flow is uniform over the section. The third assumption, the type of fluid that we are considering is in this case is an incompressible fluid, and it also follows the Newtonian's law. Now let's now analyze. Looking at the schematic on the board, you will notice that the heights at state 1 and state 2 are uniform. Then also the diameter at 1 and 2, they are also uniform. So going back to your continuity equation, which is given as Q equals to V1 A1 equals to V2 A2. For a uniform diameter, D1 is the same thing as Z2. So automatically, A1 is the same thing as what? A2. So we are left with what? V1 equals to what? V2. Are we together? So which means wherever we set our eyes on V1 is the same thing as what? V2. So this equation, let's name it equation 1. Then here we have equation 2. And here we have what? Equation 2a. So we can easily substitute equation 2a into equation 1 to reduce the equation, which means V1 and V2 will be eliminated from equation 1. Similarly, when you look at the heights of 1 and 2, they are also what? At the same level. So we eliminate Z1 as well, Z1 and Z2. So equation 1 becomes P1 over rho plus, I'm sorry, we need to add head loss at this level. The reason being that as you discharge water from pipe 1, moving from pipe 1 to pipe 2, it depends on how the structure of the pipe is. That one will now be what we are going to analyze once we are done with the major head losses. We are still going to look at some minor head losses that occurs in pipe. At the exit level where you are discharging the water to, there is a form of head loss. So you need to add head loss at the exit level. So going back to equation 1, since you have neglected some terms, Z1, Z2, V1, V2, equation 1 reduces to P1 equals to P2 over rho plus the head loss in the pipe. So automatically the head loss becomes HF equals to P1 over omega minus P2 over omega. Note this as equation 3. The next thing we are going to do is to look at all the summation of the pressure forces that occurs in the pipe. Summation of all the forces that occurs in the pipe. At this level, we have this to be coming in, and at this level, this one is going in the other way round. So the pressure force simply means you are going to get it from pressure equals to what? Force over area. Are we together? So at this level, we have P, the pressure at stage 1, multiplied by the area at stage 1. Since they are moving in counter, or they are moving in opposite direction, so P1A1 minus P2A2 equals to F. Note this equation. Going back to the assumption that we took initially, which we said D1 equals to D2, definitely A1 equals to what? A2. So we are going to eliminate A out of, we are going to make A in this case as, since A1 equals to A2, which is the same thing as A. So we have this equation to be written as P1 minus P2 multiplied by A equals to F. So we have P1 minus P2 equals to force over what? Area. So we have pressure at this level. The next thing, we want to make this expression, let's name it as equation 4. We want to make it to come in the form of this. Omega is defined as density multiplied by acceleration due to gravity. So we need to insert it. We want it to equation 4 to look like equation 3. Then we come back here, we have P1 minus P2 divided by what? Rho G, which is the same thing as force divided by what? Rho G. Whatever you do at the left side, you must do it at the right side. So we have Rho G multiplied by area. Now for the friction force. The friction force is defined as pi dl multiplied by the friction factor. Pi dl multiplied by the friction factor. The frictional resistance F equals to the friction factor multiplied by pi dl multiplied by V square. Multiply by V square. So we have equation 5. So now substitute equation 5 into equation 4. So we have, into this equation, we have P1 minus P2 divided by rho G equals to F prime pi D L multiplied by V square divided by rho G H. Note that we have already defined this term to be something. We define it as equation 3. So you can change it back to equation 3. So we have HF equals to F prime pi D is defined as the perimeter of the what? Of the pipe. So you can change pi D to perimeter. Let's put a dot to differentiate it from pressure. So we have L, we have V square over what? Rho G A. Rho G A. So what are we looking for? We want to make the expression to be of this form. Mi. So we need to make V the subject of the formula. V square will now be H subscript F multiplied by rho G multiplied by A divided by F prime PL. Now we are going to bring out some terms out of this expression. Look at how I'm going to go about it. Height in this equation is defined as the edge loss per unit length. So we can easily bring this out as I. The next one is the hydraulic mean radius, M. M equals to the remaining thing that you are seeing here is the value of your M, apart from rho G, this. We have already defined what M is. M is what? A over what? P. So A over P, no. A over P is M. H over L is I. So M is A over P. Then the last term that you are seeing in the equation is representing the Chezy constant C. So C is what? Is what? Rho G over F prime. Thank you very much. So let's just make it as square root of rho G over FL. You are still going to see it now. Now let's go back to the equation and substitute these three terms into V. You know V becomes what? V equals to square root of everything. So let's differentiate it now. Square root of what? HF over L. HF over L multiplied by square root of G over what? Over F prime. Rho G over what? F prime. And the last one is dot A over M. A over M. If you notice this equation is taking the form of what I have written there. So we have it as we are still coming there. I'm still going to simplify it to that level. Just calm down. So at this level, What happened to this gentleman? He will still be in the square inside the square root. Then what happened to this gentleman? It will also be inside the square root. Then the only one that will be out is this gentleman. Then when you find the square root, you have it as ordinary C. So the final equation now becomes V equals to C into bracket MI. So that is the derivation of Chezy formula. Now let's solve an example. Example 1. In a pipe of diameter 350 mm and length 75 meter, water is flowing at a velocity of 2.8 meter per second. Determine the edge loss due to friction using 1. Darcy Weisbach, 2. Chezy formula. Note: assume kinematic viscosity of water as 0.012 Stokes and take Chezy constant C to be 55. Let's solve the problem. Now, what are the data given in the question? The diameter of the pipe D 350 mm, the length of the pipe 5 meter, (75 meter). The Chezy constant C is 55. Then kinematic viscosity is given as what? 0.012 Stoke. Velocity 2.5 meter per second. 2.8 rather meter per second. Now let's look at the parameters that we have on the board, whether all the units are in conformity. 1. Millimeter and meter. So we need to convert millimeter to what? Meter. So we divide by 1000, we have it as 0.35 meter. Stokes. We convert Stokes to meter square per seconds. And when you are converting this, you divide it by 10 raised to the power of minus 10 raised to the power of 4. You divide it by 10 raised to the power of 4. So it becomes 0.12 times 10 raised to the power of minus 4. The velocity is okay. The SI unit of velocity is okay. The next thing is the unknown. Let's define the unknown. Find. What are we asked to determine? We are asked to determine the edge loss in 2 stages for Darcy Weisbach and Chezy formula. The next thing is assumption. Assumptions. Assumption 1. Water is modeled as an incompressible fluid. Water is modeled as incompressible fluid with a constant density of of 1000 kilogram per meter cube. After the assumptions, we move to the schematic. Let's bring out the schematic of how the problem looks like. Schematic. It is a pipe that has length, it has diameter, then it also have the speed at which the fluid is moving in the pipe. So this is the diameter. The diameter is 0.35 meter. The speed at which the water is moving is 2.8 meter per seconds, and the length of the pipe is taken as 75 meter. So we are done with the schematic. Then also density 1000 kilogram per meter cube. Then kinematic viscosity, which is taken as 0.012 over 10 raised to the power of 4. What is the next thing that we are going to do? Is to write out the governing principles. The governing principles are Darcy, Weisbach and Chezy constants. The next one is write out the governing equation. Governing equation. We have Darcy Weisbach. For Darcy Weisbach, we have HF 4FL V squared divided by D multiplied by 2G. And for Chezy, we have V equals to C into brackets MI. After we are done with this, we now analyze. We start solving the problem. Analysis. Analysis. Starting with Darcy Weisbach, we have in the question, we are given the length, we are given the speed, we are given the diameter, but something is missing here. The friction factor is missing. So we go back to the equation I gave you previously. The friction factor F is 0.0791 divided by Reynolds number raised to the power of 1 over 4. 0.25, 0.0791, 0.0791. If I have given 0.00791 before, correct the value. It is 0.0791 divided by Reynolds number raised to the power of what? 1 over 4. So how do we determine the Reynolds number? The Reynolds number is expressed as this. We need to determine the value of Reynolds number before we can determine the friction factor F. Reynolds number is given as the density multiplied by speed multiplied by the diameter divided by what? Dynamic viscosity. Now something is missing. Dynamic viscosity is missing. We are only given kinematic viscosity in the question. So we can look for a way to bring out a relationship between kinematic viscosity and dynamic viscosity. So dynamic viscosity mu equals to kinematic viscosity equals to dynamic viscosity divided by density. So when you come back to the Reynolds number expression, when you substitute this value, it becomes Reynolds number equals to UD divided by what? Kinematic viscosity. Are we together? Now, let's now insert. Our next step is to insert the parameters value given. So we have U is given as 2.8 multiplied by the diameter of the pipe 0.35 divided by the kinematic viscosity 0.012 times 10 raised to the power of, not minus in this case because it's having this, divided by 4. If you are taking it up, it becomes minus. So when you punch your calculator, what's the value at this level? 8.167 times 10 raised to the power of 5. Are we going to add any unit to this? No, because it is a dimensionless what? One of the dimensionless quantities. So the value of the Reynolds number is determined as this. So we go back to the friction factor. We can determine F now. F now becomes 0.0791 divided by 8.167 times 10 raised to the power of 5. All raised to the power of 0.25. 0.00263. That's the friction factor. Now, what are we going to do now? We are going to go back to the equation of Darcy Weisbach and substitute all the values. So HF becomes 4 multiplied by F. F is 0.00263 multiplied by L. L is given as 75. Then multiplied by V, 2.8 raised to the power of 2 divided by D, 0.35 multiplied by 2 multiplied by 9.81. So when you punch your calculator, you will notice that the final result becomes 0.9 meter. So this is the head loss due to Darcy Weisbach equation. Then for the second thing we are asked to determine from the question, we are asked to determine the head loss using Chezy formula. For Chezy formula, we have V equals to C square root of MI. In this case, V is known, C is given. We have two unknown. The two unknown is M and I. Note that M is defined as the hydraulic mean radius. So M is equals to the area of the pipe divided by the perimeter of the pipe. When you further simplify, we have it as pi over, we have it as D over 4. D in the question is given as 0.35 divided by 4. Please. 0.0875. That is the unit of the hydraulic mean radius. Then the next one is to determine the head loss per unit length. I equals to HF over what? L. And this is what we are asked to determine in the question. So which means we can leave this in this expression. We can substitute this into this expression. We have V equals to C square, then M multiplied by what? HF over what? Length. Make HF the subject of the formula. This gentleman comes to this side. HF equals to V multiplied by L over what? C square M. Now insert the values into this equation. So we have V. V is given as what? 2.8 multiplied by the length of the pipe, which is 75, divided by 55 square multiplied by 75. When you punch your calculator, what is the final result? M 0.085, 0.0875, 0.79 meter. Now we have calculated head loss using Darcy, Weisbach and Chezy constants. Now, if you look at the calculated value, you will notice that what we got for Chezy is quite different from what we got for Darcy, Weisbach. This is only based on two reasons. Number one, it is based on conceptual reason, and it is based on the mathematical equation that is given. On conceptual reason, when you look at it, we made use of friction factor in Darcy, Weisbach, but in Chezy case, we are given Chezy constants as what? Chezy constants as 55. That one is based on conceptual and on mathematical reason. For conceptual reason, both are used for calculating head loss. But when you look at it, F is given. I think that is the first thing I mentioned. F is given, which we calculated for, and C is given in the question. On mathematical basis, we have their formula to be quite different. So for Chezy, this is for Chezy, and this is for what? Darcy, Weisbach. Now we are going to look at the minor head losses in pipe. The minor head losses in pipe comes into 7 categories. The first one is head loss at the entrance of the pipe. That's the first one. The second one is head loss due to sudden enlargement of the pipe. The third one is head loss due to sudden contraction of the pipe. The fifth one is head loss due to an obstruction in the pipe. The sixth one, head loss due to bend of the pipe. And lastly, head loss due to various fittings in the pipe. Now, I would have loved to give some of the mathematical expression of what I have said above, but we are going to see this when we are analyzing pipe networking. Pipe networking comes in 2 different categories. We have a series arrangement of the pipe, then we also have a parallel arrangement of pipes. A pipe networking is a system of interconnected of different pipes together. A typical example of what I'm talking about is this. When you have a pipe, this is a pipe 1. When you connect another pipe to it, this is another pipe connected to pipe 1. We can also connect another pipe to pipe 1. Making how many pipes? 3 pipes. 1, 2, 1, 2, 3. At this level, the mass of the fluid that is entering at point 1 is the same thing as the mass of fluid entering at 2 and 3. Or the discharge at Q1 equals to Q2 plus Q3, which is also known as V1A1 equals to V2A2 plus V3A3. This expression is from the continuity equation. Now let's look at a simple schematic that shows some of the things that I have mentioned concerning the minor head losses in pipe. We have a reservoir, that is discharging water to pipe 1. All of a sudden, pipe 1 enlarge. It enlarges to pipe 2. Also, at the exit of pipe 2 also what? Contrasts. So this is pipe 1, pipe 2, pipe A, pipe B, pipe C. At pipe C level, there is an obstruction that occurs at this point. There is a stone in the pipe that doesn't allow the water to flow the way it ought to flow. So the next thing is the water is being discharged into another reservoir. So we want to look at some of the head losses, minor head losses that occurs in this pipe. So we can let's name it as 1, 2, 3, 4, then back to 5. At this level, we are going to consider 2 key things. We are going to look at the major head losses in the pipe as well as the minor head losses that occurs in this pipe. For this pipe, for the first pipe, which is pipe 1, for the second one, pipe 2, pipe 3, pipe 4, what are the major head losses that occur? Now, let's start our analysis using Darcy Weisbach. Darcy Weisbach is given mathematically as HF equals to 4F L V square over what? D multiplied by 2G. For pipe 1, what will be different at pipe 1? The length of the pipe and the diameter of the pipe. Also, if you are given the friction factor from these 3 stages, you can also include it there. But in a situation whereby they have a uniform 1, it means you are taking F as 1. Now, for pipe 1, HF1 becomes 4F1 L1 V1 square divided by D1 multiplied by 2G. Then for 2, HF2 FL2 L2 B22 over what? D2 multiplied by 2G. For the third case, HF3 4F3 L3 V3 square divided by D3 multiplied by 2G. And for the 1, 2, 3, 4, which is also the same. This is pipe 1, pipe 2, pipe 3. But the only thing at this level is when we are considering the minor losses. That's where we are going to look at this. But in a situation, you have to add up all the major head losses together. So you have H total of major. It becomes something is common to these 3. 1, 2, 3. 4 is common and 2G is common. So we have 4 over what? 2G into brackets F1 L1 V1 square plus over D1 F2 L2 V22 over what? D2 plus F3 L3 V3 square over what? D3. These are all the major head losses that occurs in the series arrangement of the pipe. Now let's look at minor head losses for each stages. Now, this is a reservoir. The water is coming from this reservoir, is entering into pipe 1, pipe 2, pipe 3, and there is an obstruction from 3 to 4. How do we go about this? At the entrance of the pipe, it has its own mathematical representation. So head loss at the entrance of the pipe is given as 0.5. At this level, what is the V at this level? V at this level is V1 square over 2G. That is at the entrance. So what now happens as the water is leaving pipe 1? This is pipe 1, pipe 2, pipe 3. As the water is leaving pipe 2, what happens in such case? There is what? A sudden what? Enlargement or expansion. So at this level, we have it as for head loss for sudden enlargement, entrance, enlargement, we have it as V2 to what? V3. V2 minus V3 divided by 2G, all power of what? 2. That is for enlargement. Then the third one, as it is leaving 3, is coming to 4. There is something inside it. Yes or no? Yes. There is an obstruction in the pipe. Now let's move on, please. For obstruction, AOB obstruction. So we have it as A over A minus A multiplied by V at this level, V4 square over 2G, then 1 over C subscript C. C subscript C is known as coefficient of contraction. Then at the final state, as 4 is coming to 5, what happened to 5? 5 is exiting the pipe. So at the exit level, H exits equals to V5 square over 2G. So the summation of all the head losses is what we are about to do now. We have 1, 2, 3, and 4. So we add up everything together to have another new equation. So the total minor head losses becomes at the entrance level 0.5 V1 square over 2G plus, when the pipe enlarge, V2 minus V3 over 2G. When there is an obstruction in the pipe, we have it as 1 over coefficient of contraction, A over capital A minus small a, V4 square over what? 2G, and at the exit level, we have it as V5 square over 2G. So this is for the total minor head losses that occurs in the pipe. So if you are asked to determine the total head losses, the total head losses will be a combination of the major and the minor. Now the total total head losses becomes H major plus H minor. So H major, let's name it equation. Let's name this equation 1, and this one becomes equation 2. So you had equation 1 and equation 2 together. You have the total head loss in the pipe. Now we have come to the end of the class today. So by next week we are going to continue from where we stopped. Thank you for listening.